Because of the fundamental theorem of calculus, every derivative formula that you know also gives you an antiderivative formula, which is essentially an integral formula. So it really pays to keep in mind all of the derivatives and antiderivatives that you already know. There are lots of derivative formulas that we know that we use frequently enough that we sort of know them without having to think too hard, but there are some lesser used antiderivative formulas that it's a good idea to keep in mind. So let's look at some examples. So let's start by calculating this integral. So integral of 2x plus 3 times e to the x squared minus 3x dx. For this one, I hope it occurs to you that because of the exponential, maybe we should do a u substitution and let u be the stuff in the exponent there. So let's let u be x squared minus 3x. That means du is 2x minus 3 dx. And we have a, oops, I probably wanted a plus here when I wrote down this problem. That would make this a plus and this a plus. We have a plus here, or a 2x plus 3 to work with. So we can put 2x plus 3 together with dx and make du, so this substitution is going to work after my little modification, and that's going to give us e to the u. So we need to come up with an antiderivative of e to the u. In other words, we're looking for a function whose derivative is e to the u, and that one probably you remember without me needing to remind you, it's e to the u. But remember, because this is an indefinite integral, we need to add our constant of integration, so plus c. And also because it's an indefinite integral, we need to undo the substitution, so that gives us e to the x squared plus 3x, all plus a constant. Okay, and we're done. So here the derivative formula that we used is the derivative of e to the x is e to the x. And that means that the indefinite integral of e to the x dx is e to the x plus a constant. Of course, we use this formula with u's instead of x's, but right, you can put any variable in here and this still works. There's another derivative formula for exponentials that you might not use as often, but depending on the context can be pretty handy to know. And that is that the derivative with respect to x of any base to the x it's what you would expect, that base to the x, but you get a factor of the natural log of the base. Okay, so if you have a base that isn't e, then this formula can save you from doing a bunch of algebra and chain rule if you ever take a derivative. So let's see how we can use this. Suppose that we have a bacteria culture that has a growth rate given by this formula, 30 times 2 to the t over 4, and that's cells per hour. How many new cells appear in the first 5 hours? So the first 5 hours, I guess that means from t equals 0 to t equals 5. And we want to know how many new cells appear, so I guess that's a change in the population. So we're looking for a change in the population over a certain time. Oops, I wrote 0, but meant 5 here. We're looking for a change in population over a certain time, and the so-called net change theorem says that the change in population is the integral of the derivative of the population function. Of course, this is from 0 to 5. But the rate of change of the population, that's the growth rate, which we have here. I called it r of t. So what we really need here is just to integrate from 0 to 5 r of t dt. Okay, so this is the integral from 0 to 5 of 30 times 2t over 4 dt. All right, well, we can move this 30 outside of the integral to start with. So 30 times the integral from 0 to 5 of 2 times t over 4 dt. And to handle this over 4 in the exponent, there are a couple ways to do this. You might be able to just guess an antiderivative, but if you aren't as good as guessing antiderivatives as some other people, then maybe it would occur to you to do a substitution. So let's let u be t over 4. That means du is 4 dt, 1 over 4 dt. And so that means 4 du is equal to dt. And so now we can do this substitution. So this is 30 times the integral of, let's change our bounds from t bounds to u bounds. So when t is 0, u is 0. And when t is 5, right, remember we're going to use this substitution formula to translate our t bounds into u bounds. When t is 5, u is 5 over 4. Okay, and then the integrand is 2 to the u times dt, but dt is 4 times du. And now we can move this 4 outside, and 30 times 4 is 120. Okay, so 120 times the integral from 0 to 5 over 4 of 2 to the u du. And now we can go ahead and guess an antiderivative. When you take a derivative of 2 to the u, you get an extra factor of natural log 2. That's what we said way up here. Right? You get when you're taking a derivative, you get an extra factor of natural log of the base. So when you're taking an antiderivative, you need the opposite of a factor of the natural log of the base. So that, I guess that's going to be 1 over the natural log of the base. So 1 over natural log 2, 2 to the u, from 0 to 5 over 4. If you're unsure about this sort of thing, remember you can always check your antiderivative by, over in the margin somewhere, taking the derivative of your antiderivative, and you should get back to your integrand. So just to check, let's take the derivative with respect to u of 1 over natural log 2 times 2 to the u. So we can move this constant multiple outside the derivative, and then take the derivative of 2 to the u, which is 2 to the u times natural log 2. These cancel. You get 2 to the u, which is what the integrand started out as. So our antiderivative is correct. All right. So let's see, gathering up these constants, we get 120 over natural log 2. And then we have to plug in these bounds. So we get 2 to the 5 over 4 minus 2 to the 0, which is 1. And then if we were actually interested in this number, we could dump it into a calculator to get a decimal approximation. There is another integral or another antiderivative formula that's really nice to keep in mind that we know, and it involves reciprocals. So let's look at this one. So let's find the antiderivative of 1 over 4x minus 3 dx. And one of our rules of thumb for good substitutions is if you have a denominator, often the denominator makes a good choice for u. So let's let u be 4x minus 3. That means du is 4 dx. So maybe we should move this 4 to the other side. We get 1 over 4 du equals dx. And now we can do our substitution. So this gives us the integral of 1 over u times dx, which is 1 over 4 du. And we can pull that 1 over 4, that constant multiple, outside of the integral. 1 over 4 times integral of 1 over u du. And now we need to think of a function whose derivative is 1 over u. But that's natural log. So hopefully that was one that you didn't need the reminder for. But just in case you did, the derivative of natural log is 1 over x. Derivative of natural log x is 1 over x. So the antiderivative of 1 over u is natural log u. Depending on the context you're working in, you might want to put absolute values here, but usually it's not super important for various reasons I don't really want to get into, having to do with the continuity of these functions. plus a constant. Of course, this was an indefinite integral, so we need to add our constant of integration, and we need to get back to the original variable, which was x, so we need to undo the substitution. So 1 over 4 times natural log of, what was the original substitution? Right, 4x minus 3. So we need 4x minus 3 in here, plus our constant all the way on the outside. And there we go, we're done. So this derivative formula, the derivative of natural log x, gives us the antiderivative formula. Integral of 1 over x dx is natural log x. And for various reasons, often you want an absolute value there. Okay, there is one important thing to keep in mind with natural logs. So let's look at this example, integral of 1 over 1 plus x to the fourth. Once you get used to using this integral formula that the integral of 1 over u du is equal to natural log of u, it's sort of a common thing that I see that people will sort of jump to conclusions and say, oh, well, if you have 1 over anything, if you integrate 1 over anything, the integral is the natural log of the stuff in the denominator, plus a constant, of course. So let's check that. Let's take the derivative of our supposed antiderivative, natural log absolute value 1 plus x to the fourth plus a constant. Let's take the derivative of that and see if we get back to the integrand that we started with, which is 1 over 1 plus x to the fourth. So the derivative of natural log absolute value, that's 1 over, and then the chain rule says we have to put this inside piece inside, so down here, 1 over x to the fourth. So everything is looking okay at first, but remember the chain rule says we have to multiply by the derivative of this stuff inside. So we need to multiply by the derivative of 1 plus x to the fourth, which is 4x cubed. And then, of course, the derivative of c is 0. So what we get is 4x cubed over 1 plus x to the fourth. But that is not the integrand that we started with, right? So something has gone wrong. And what has gone wrong is that this antiderivative is just not correct, okay? If your denominator is not just the variable, then you can't use this integral rule, okay? You have to do some other technique to figure out what this integral is. And what technique you use depends on exactly what is in this denominator. But if this denominator isn't just the variable, don't jump to conclusions about natural log. Of course, you can guess that this is the correct antiderivative, but you should check your guess. Right? In this case, we caught our mistake because we checked our guess. So be careful about antiderivatives involving natural log.